safe human-robot collaboration with risk-tunable control barrier functions. Innovations and challenges. In human-robot collaboration or HRC applications, ensuring the safety of humans is of paramount importance. Moreover, the complexity of human behavior and the errors in sensors necessitate robust safety measures. Traditional safety solutions often involve physical barriers or rigid safety protocols, which limit the efficiency and dynamic maneuvers between humans and robots. A summary of contributions. We introduce a new risk-tunable control design framework that modifies robot trajectories based on the risk tolerable using uncertain control barrier functions, or UCBF-based safety constraints to ensure safety in HRC tasks. We use an optimization-based controller where the objective represents the robot working on the desired task by following the reference trajectory while subjected to a probability satisfaction constraint over the safety under uncertainty condition. These safety under uncertainty constraints are represented using uncertain control barrier functions, or UCBF. This is where we introduce the notion of tunable risk through the probabilistic safety constraint and give a sampling-based solution that probabilistically guarantees safety. Design methodology. Here, we summarize the mechanism of our risk-tunable safe HRC. We share the human and robot positions to the controller block on the left along with the robot reference trajectory information. Then, the controller constructs the UCBF-based safe control set by taking samples of the uncertainty in the human position, which contains all the control values that guarantee safety. Now, to guarantee safety under uncertainty, we collect a sufficient number of samples of uncertainty and then consider the corresponding safe control sets to compute our control value that will render the safe set forward invariant under the robot dynamics. Hardware experiments. We run our hardware experiments on a Franka Panda 7-link manipulator. We use OptiTrack camera system to track the human in the robot neighborhood. Case 1. Obstacle avoidance. We begin with the case of obstacle avoidance case study where the robot is supposed to finish a pick-and-place task. Here, we also compare our method with RRT and characterize the task completion time vs. risk trade-off using simulation experiments. The reference trajectory without a controller can lead to dangerous situations. We tested the experimental conditions under the safe controller. Benchmark with RRT methods. The trajectories are similar, but the RRT computation efficiency is low. Case C2. Different safety distances. We then repeat the above hardware experiment with different safety distances ds to ensure that the robot completes its task while guaranteeing safety under different safety tolerance specifications. In case 3, this is another fundamental yet important HRC task, where the robot hands over an embedded board to a human who is in motion, requiring the robot to maintain a close but safe distance from the human. Similarly, in tasks where tools are handed to humans, the reference trajectory poses a collision risk. We tested the experimental conditions under the safe controller. Conclusion and future work. We conclude this presentation with our findings and the future directions. 1. We validated the algorithm in both simulation and hardware platforms with different HRC test cases. 2. We only noticed a marginal deviation of 5 mm between simulation and hardware safe trajectories at any time step. 3. We also characterized the trade-off between risk and task time, highlighting the flexibility of our algorithm. 4. In our comparison experiment, the Risk-Tunable controller outperformed RRT by performing at 10 Hz compared to 4 Hz with RRT. 5. With our controller, the robot can arbitrarily close to the human, showing potential for being used in many HRC tasks. 6. As a future direction, we intend to combine a learning algorithm that predicts human intent with our proposed controller for a faster and more precise safe HRC algorithm.